Hi everyone. This lesson's the second part of representing and using data. So before, in the first part, we looked at the mean and the median and histograms and ways of kind of representing data. Now we're going to look at how we can analyze data. Specifically, we're going to look at something called standard deviation. And we're also going to look at coding data, which is ways we can change data to make it easier to read. So what we're going to cover, we'll look at standard deviation to start with, what it's about. We'll look at calculating a few statistics and calculating the standard deviation, and then we'll move on to coding, how the coding actually affects the mean and the standard deviation. And as always, we'll finish off with an exam style question so you can see what to expect at the end of the year. So what's the standard deviation all about? Well, it tells us how spread out data is. So I've got two example data sets for you here to give you an example of something with a high standard deviation and something with a low standard deviation. So this first data set, A. In fact, both these data sets have exactly the same mean. It's a good starting point. They both have a mean of 100. I'm not going to show it now, but you can do it by adding them all together and dividing by however many numbers there are. But they have different standard deviations. Can you see that in this first data set, A, all the numbers are very close to 100. I think the furthest away from 100 is that 105, so they don't tend to get very far away from the mean. Because of that, the data is not very spread out, and we'd say it's got a very low standard deviation. Compare that with the second data set, where there are some numbers that are very far away from the mean, so you've got 153, 58 there. Even though the mean's the same, this is very spread out from that mean. Lots of the values are very far away from the mean. So we'd say this has got a high standard deviation. And we can graphically represent that as well. These are probability distributions, these graphs, and they kind of represent what data looks like. So the area under these graphs gives the probability. So under both of these graphs, the area is the same. It's 1 because the sum of all the probabilities is always 1. You don't need to know too much about probability distributions other than that they kind of look a little bit like this. And this first one has a very low standard deviation. Can you see how most of the data is very near the middle? In both cases, this middle point, that middle line, is 100 because both of them have a mean of 100. But this one, that rises very quickly and all the data fits in very close to 100, whereas for the second one, it's much more spread out so that lots of the data actually lies quite far from the mean. So this is a way of graphically representing distributions and gives us an idea of what the standard deviation is. So let's move on to doing some calculations. First one we're going to look at is SXX, which is a summary statistic. By itself, to be honest, it doesn't mean a great deal. It's really an intermediate step for calculating lots of things, but one of those things is the standard deviation. So we're going to take our second data set, the one we said we think has quite high standard deviation, and we're going to calculate SXX. That's the formula. Looks pretty nasty, but the first thing to say is that it's given to you in your formula book, so there's no need to remember it. And also, it's not really too bad to apply. I'll talk through what each of these bits mean. So the sum of x squared part is each of the values squared and then added together. So I've given the first part of the calculation here. It's 105 squared plus 86 squared plus 153 squared, and then we do plus 95 squared plus 64 squared plus 127 squared, and so on and so on. So you just square each of the numbers and then add them together. Remember this symbol here, which we've seen before, means sum. So it means we're going to sum all the values of x squared, and these are our x's here, these data points. Now, it's important to see the difference between what we've just done, the sum of x squared, and what we're about to look at, which is sum of x squared. Okay, there is a difference. For this second one, we're adding all the numbers together, we're doing the sum of x, and then we're squaring the result. Now that is different to squaring each of the numbers individually than adding them together. Okay, you will get a different answer and it will be significantly different. So remember in this second one, add them all together first, then square them. For the first one, square each of the numbers and then add them all together. Okay, so be really clear about what each of these things mean or you'll end up making a mistake. N is the same as it's always been. It's just the number of items of data, just like it was when we were calculating the mean and things like that. So there's 10 numbers here, so n's going to be 10 for us. And as I said, this whole formula is given to you in the formula book, so don't fret about memorizing it. So I've calculated these values for this data set, so we don't have to add loads of them together. So the sum of x squared we found was 108,154. The sum of x was 1,000, and there's 10 points, so n is 10. We can throw all those in the formula and get a number out. So you just stick this in your calculator, and you'll get 8,154. In fact, some calculators will do this calculation for you if you just give it the data points. I'll try and do a separate sort of additional video content lesson on how you can use a calculator to find certain statistics, including the standard deviation. It can be a very good check. Sometimes it's not such a good idea to do the whole thing in your calculator, because if you make one little mistake, you can end up getting no marks, which is not what you want. But I'll do a bit about how we can use our calculator to help us out with these calculations. So moving on to the standard deviation, all we do is the square root of that SXX we calculated in the previous part and divide by n, the number of data points. So as you can see, SXX was kind of like a halfway step to getting us to the standard deviation. So let's take that data set again. If you remember, we found SXX was 8,154, and we know there's 10 data points. Stick them in the formula and you find the standard deviation is 28.6. Easy as that. A quick note on notation. So we sometimes write SX for the standard deviation of X. Yeah, standard deviation of all these data points X. You may also see sigma used for the standard deviation. There is a distinction here. It's quite, it's a little bit difficult. You don't need to know a huge amount about it, but SX, we normally say this is the standard deviation of a sample. Okay, so we did a little bit about sampling in a previous lesson, whereas this is the standard deviation of a population. So the standard deviation of the whole population, everything in the population. So they are slightly different, but they're both standard deviations. We have the same thing with calculating the mean. X bar is the standard deviation of a sample, whereas mu, which you may also see for the mean, is the standard deviation of a population. Okay, so just bear that in mind, but to be honest, you don't really need to know too much about that distinction. We can roll the two formulas into one. So it looks really nasty, that bottom formula, and to be honest, I wouldn't recommend you use it because it's not actually given to you, whereas the other ones are. But because SXX is this, as we saw in the previous step, if I substitute all of this into here, I get this bottom formula when I tidy it all up. So it's a way of missing out calculating SXX. So that's a direct formula for the standard deviation. But to be honest, you're better off calculating SXX and then calculating the standard deviation, because both this formula and this formula are given to you in the formula book. So just do it in two parts and it'll mean you get the right answer much more often, I'd say. So I think that's the way to do it. Again, your calculator can calculate the standard deviation if you give it the data points and you know how to do it. And we'll have a look at that another time. So let's have a look at the standard deviation and calculating it for two data sets. So this is the data set we said had a low standard deviation right at the start. Everything's quite close to 100. Now I've calculated the sum of x squared and the sum of x so we can do some calculations. I've written the formulas for us at the bottom down here. So if I apply this first formula, I can find SXX, and we find that 68. I'm not going to run through this. I'll let you do it by yourself, but all I've done is calculated these and run it through that formula. That's something you can have a go at to make sure you understand how to use the formulas. I can use that second formula to figure out the standard deviation, and I find it's 2.61, which is pretty low. In comparison, here's the data set which we said we thought was quite spread out, and it had a high standard deviation. I can find the sum of x squared and the sum of x again. And we actually did this one just before. We found SXX and we found the standard deviation. And you can see, indeed, it has a much higher standard deviation because the data is much more spread out. So hopefully you can see how that ties in with what we see in data that is much closer together, and therefore it has a higher standard deviation. And using these formulas, we can actually calculate the values. So see if you can reproduce those results, and be careful with the distinction between this, which is squaring the values and adding them together, and this, which is adding all the values together and then squaring them. It's really important you understand the difference. Tiny little bit here on variance. It's another measure of how spread out data is, and it's just a standard deviation squared. It's as simple as that. It's just something else you need to know what it means. So what we do is we take Sx, which was the standard deviation, and we square the value. Because the standard deviation, the formula was Sx is the square root of Sxx over n. If we want the variance, we square that, gets rid of the square root, which is why the variance formula is that. Okay, so just something to be aware of. It's not really any different, it's just a slightly different measure of how spread out data is. If you get asked to work out the variance, that's how you do it. All you do is just square the standard deviation. Or if you're given the variance and you want the standard deviation, we square root the variance to get the standard deviation. We also need to be able to get standard deviation from tables of data. There's a formula to do it, and it's not very nice, I'm afraid. It's also not given to us. Okay, so you need to really memorize this formula. It's not a very nice one. You take the sum of fx squared, we'll talk about what that is in a second, divide by the number of data points and subtract the mean squared off it. Let's have a look at an example to see how to do that. So I used this same data set in the last lesson where we calculated the mean. Now we're going to figure out the standard deviation. What I've got is an extra column on the end. Hopefully you recognize this midpoint column. It's just the middle of 0 and 30, so 15 is the midpoint. And this is just the frequency times the midpoint, so 8 times 15, which gives us 120. This third one, though, or the fifth column overall, is new. Now that one is the frequency times the midpoint squared. Okay, so for this first row, for instance, we'd do the frequency, which is 8, times the midpoint, which is 15 squared, and that will give us 1800. So hopefully you can see how we're calculating that. And that is how we figure out this top line of the formula here. So I figure this out for every row, and then because I'm doing a sum, add them all together. So I've put the sums there. So the sum of the frequency, that's n, remember, because it's the number of people. The sum of fx, we need to calculate the mean, and this is the sum of fx squared, which we need for the standard deviation. So hopefully you remember this is the formula for the mean. We do the sum of fx and divide by n. So we just add up all this, get 3745, divide by 50, there's your mean. Now the standard deviation, all I'm doing is filling in the formula here. The sum of fx squared is the sum of that column. It's that 383425 figure. Divide by n and subtract the mean squared. And there's our value, standard deviation. This is a little bit tricky, but if you memorize the formula and just kind of understand this this table layout where we've got the midpoint, fx and fx squared, you'll be fine at calculating this. It's really not too bad. Often they'll give you things like the sum of fx squared because it takes so long to work out. They'll just give you the value, okay? But they don't always, so it's important that you know how to do it from the data itself. Again, if your calculator is clever enough, it will be able to do this for you.